right, good morning. How is everyone? Good. Cool, glad to hear it. All right, well, even though I said I wouldn't get to homework 8 until later this week, I actually managed to get it all graded yesterday. It's your birthday, happy birthday, yeah, and happy last day of school for a few days. That's awesome. Yeah, I won't sing happy birthday to you. Yeah, so I got homework 8 graded, and the honest truth is, so many people did so well on it. It was really, really fast to grade. Because I mean, I gave you the test cases, and if it worked on that, then it was pretty much just eyeballing the code, seeing what you did inside, and so I got through all the grading last night, which was great. So grades are posted, and by and large, people did really well, as I suspected they would. So that's good. Homework 8 was another exercise in Bash, and it was also, introducing this idea of an associative array. There were a few people who did this without associative arrays and used things other than offset and tr, which I said wasn't allowed. But I let you do that anyway if you used some different approach. But make sure you understand associative arrays, right? They will almost certainly be on the final exam. And they're a really powerful concept. They're a good thing to have in your bag of tricks. And we'll definitely spend time, the remaining 2 courses talking about them and working on them. So they'll be back. So if you didn't use associative arrays for homework 8, make sure you go back and think about how you would do the problem with those, so that you're comfortable with the concept and the implementation. And especially in Bash, the syntax around using these things can be, well, not can be, is a little bizarre, at least to me. So let me just show some. Oh, my bad. Let me just show you some code around this. And this looks a lot like what other people turned in. Some people had shorter code than this. Some people had longer, right? Length doesn't really matter directly, but this is the general spirit of how the algorithm was outlined in the assignment. So remember, your bin bash has to be the first line of your file. If it's down here, it's not something that affects how the program is executed. It's just a comment. It's only if it's the very first line in the very first column of the file that it affects what command is used to execute the contents of this file. So that's got to be the first thing in your script. And then comment block at the top. And then declaration of the array. A lot of people declared the array inside their for loop. That doesn't seem to do any harm, but you're declaring a variable, right? And it's a variable whose value we want to persist throughout the whole script. So I would declare that at the top, right? Here's our main input loop. So while read line, some people made a loop that read all of the input and appended it to a big long variable. That's usually not a good strategy if you can avoid it, because if you had a billion lines of input, that would almost certainly blow up, right? You'd run out of resource trying to save that. Whereas trying to tally phrases in a billion lines of input might not take a lot of memory at all. right? If you only had 1,000 phrases, it's 1,000 phrases, you know, and you might see a phrase a million times. Um, that's not a problem. But trying to take all of your input in and save it in memory, usually something to avoid, right? If you can process your input as it's coming in, that's going to be a better approach, right? If you absolutely need to save that input to do something with later, then yeah, you've got no choice. You've got to save it either in memory or in a file. There was no need for temporary files in here. Temporary files, they're good if you absolutely need them, but they can be kind of dangerous, right? Because what do you call them, and can you clean them up at the end? And what if the script gets interrupted partway through? And what if you pick a temporary file name that you know clobbers a file that already exists? Or what if you're running this from a directory that the person does not have write access to? So if you can avoid making temporary files, that's usually good. If you need a temp file, there's a /tmp directory that's, you know, always available, always writable. You have to be careful with file names, but you know, you can tag the process ID and the date and something unique and probably be okay. But you could do this by processing the input on the way in, and that was the way the algorithm was described in the assignment. So that's what this does here. So while read line, so line is a single input, do, and then so here's what's going to happen. We're going to clean up the line. We're going to convert to uppercase, remove those 8 characters, change tabs and spaces to underscores, and then compress consecutive underscores to a single underscore. Right? Now I did this all in one line, right? But I've explained exactly what happens in this big long line, right? We take our input, we convert it to uppercase, we remove those characters by first changing them to an @ sign and then removing the @ sign. Yeah, so we change the characters, including a single quote, to an @ sign and remove that. And then we take spaces and tabs and we change them to spaces to underscores, and then we take consecutive underscores and change them to a single underscore. And then we change the separators to spaces. So, you know, dot, comma, colon, semicolon, exclamation mark, question mark. We change those with sed into just a single space. And then, and now we have a conditioned line, right, which has been cleaned up and is a space-separated list of phrases, and so we want to process each phrase. So this is where we use this for in statement. And phrase will be a phrase that we need to tally, right? So first thing, get rid of leading and trailing spaces, which are underscores now. And then check to see if the phrase is empty. And if it is, then that can mess up the associative array access, so we just say continue. Continue will take you to the top of your most enclosed loop, which in this case is this for loop. So the continue basically skips these lines of code. Otherwise, we do the read, modify, write. So we read the current count, we increment the current count, we save the new count. So this iterates over all of the phrases, and then this outer loop iterates over the entire input stream. And when we come out of here, our tally should be built, and so now we iterate over the keys in our associative array, and for each one, make a version of the phrase that doesn't have underscores anymore. So change those back to spaces, and then just echo in the required format. So that should work well. And again, make sure you understand kind of the magic of associative arrays, right? We can use associative arrays just like plain old arrays. We can iterate over the keys and do something with each element, but the real power of these things is when you want to access a particular value, you can just go in with a key and say, give me the value associated with this key, and it should bring it right out to you. And that's an easier way to to process code sometimes. So when I make grades for these things, I realized I spend a lot of my time grading typing in comments, right? And I find I'm typing the same comments over and over and over again, right? Your program treats illegal input as a 0. Make sure you use scanf and check the return value to see that it converted to an integer. Parentheses -10, right? And I find myself typing that, 20 times in the course of grading 50 assignments. So I have, derived from the grading rubric in the assignment, I have a file here that basically lists, each thing that can cost points, how many points they cost, and then just, a kind of semi-random code here in the beginning. So, test 0, minor or major issues, test 1, minor or major issues, test 4 issues, and things like that. So when I'm grading, right, I just run this program called add comments, and I give it that grading file, and it asks me for a code, right, and I type in something like, minor issue on 0, minor issue on 1, major issue on 3, and, a problem with commenting. Right? So as I go through and I grade, I just write down these codes in a file, and then when I'm ready to enter in Canvas, I just go through, I type in those codes, and that copies to my clipboard. Oh, boo. But you have to use the right codes. So 0 minor, 1 minor, 2 major, and 30. Right, and then I can well, this didn't work. Oh, I got stuff going on. Anyway, it works better. So yeah, I can just type in codes and it puts onto my clipboard a list of each of the deductions, how many points it's worth, and then puts at the top the total grade for the assignment. So I'm in Canvas. I just click in the comment window and I do a Control V to paste that, and then just take this grade and move it to the points column, and just kind of go from there. All right, so script not executable. So so I'm showing you that because this uses associative arrays, right? So yeah, add comments is just a script that I put together when I got tired of typing the same things over. So it makes 2 associative arrays, one for points, one for comments. It reads my input file, which is that comment file. It uses awk to break it up into 3 fields. So I have a key that I'm using for that comment, the number of points it's worth, and the comment itself. And then I use that key to store the number of points and the comment into this pair of associative arrays. And then I just go into a loop where I ask for what codes. I read those in. They're separated by spaces. If it's an empty line, then I just exit the program. Otherwise, start the grade at 100 and go through each code in the list of codes I entered, pull out the number of points, pull out the comment from those associative arrays, subtract the points from the grade total, and I just string those big comments together side by side. And when we exit this, when we're done with all the codes, then I just go ahead and I take all of that, and I put it into execl, which says take standard in, put it on the clipboard. So this took a few minutes to write, right? I had to figure some things out and I had to debug it, but it's a huge time saver, right? And it's built on this idea of associative arrays, because these codes in the beginning, I could make these consecutive integers starting from 0, and you know, that would work, and then I could just store these in arrays and look up the value. But if I want to have other names like T4 for test 4, right, then I can use these directly as indexes and pull out, you know, the point values and messages based on those. So that's you know, the kind of thing. If you have associative arrays in your bag of tricks, you start to see problems as things that can be, you know, tackled with an associative array. That's the whole idea of sort of immersing yourself in a set of tools. Same thing with awk and sed and tr and stuff like that, right? If they're available and you've used them before, you'll start to think of them when you're trying to solve a problem, and that just, you know, increases your fluency in whatever environment you're in. All right, so let's go back to talking about processes, and we refreshed ourselves on file I/O yesterday. So fopen, fclose, fgets, fprintf, and so on. So let's look at this popen. So popen takes two arguments: a command and a string that basically says what kind of I/O are you trying to do. So command is your usual null terminated string. It's a shell command that'll be executed by sh. And the type argument is similar to what we put in when we open a file. We can make an R for reading or a W for writing. So let's play with this. And I need some kind of library. Nope, just standard I/O. And it returns a file pointer. All right, so what should we do? Yeah, xclip is really handy. Somebody's commenting on how they've used xclip in chat. Xclip is just one of those utilities that's available in you know, Unix. If it's not there, you can sudo apt install xclip, and it lets you send something to standard in, and it puts it on the clipboard. And then for me, you know, I can Control Alt V inside my terminal or Control V somewhere else, and it'll paste from the clipboard. And you know, that's how I do my time stamping of the videos and stuff like that. So it's a really useful tool. Can you use it over SSH though? So I don't think it's really an SSH thing. Let me see. Because when you're copying, right, it's copying into my clipboard, right? So it's not like it has to transmit. It's really my terminal server, right? My console program is running SSH, but it just sees that. But I think the question meant something else. So let's open BC. That's our basic calculator. All right. So so we'll open that up with popen, and let's print out the value of fp. And I'm going to use a %p to print this out as a pointer so that it doesn't yell at me for trying to print it as an integer. Does the clipboard itself work over SSH? Not sure. All right, so we should be able to write something into this file pointer and have BC interpret this as input to itself. So let's just try that. So fprint fp, let's just say 2 plus 2. And then let's sleep a few seconds, and then let's exit. So let's print some messages here. So we'll say writing, done writing. All right, so here's some good debug code. So we're going to open a pipe. We'll assign the return value to a file pointer. We'll print out the value of that. We'll write to the file pointer. We'll send 2 plus 2 to BC. We'll say that we're done writing, and then we'll go ahead and exit. And I don't care about errors. Oh, too few arguments. I do care about that error. So we'll open this for writing. I'll be good. I'll go ahead and include sleep. So I want to know what library I have to include for sleep. If I say man sleep, it will show me the first chapter that contains the sleep command, which is chapter 1. That's the interactive sleep. I want to know about the function sleep, which is probably in chapter 2 or chapter 3. Feels like a pretty high level thing, so I'm going to look in chapter 3, and that tells me that's the sleep function. There's the include that I need to have. So I'll put that in. All right, now we got a nice clean compilation. All right, you ready to run this? So we're going to open up a BC command with a pipe and send 2 plus 2 to it. So we take P1, we open the pipe, we write to FP. We're done writing to FP. Nothing has happened yet. And then when the program exits, it prints out the result from FP, which is 4. All right, this is that buffer that we talked about yesterday. So this is buffered output. Okay, when we do this write into the pipe, it doesn't immediately go into the command. It hangs out in a buffer until our program exits, and then it gets flushed. So what we can do up here is force after the printf, do an f flush. So that the thing on the other end of the pipe actually reads, actually sees 4 characters of input. So if we do this, it should output before the program exits. Right, so there's our 4 right there. And then our program hangs out and sleeps for a while, and then eventually exits. Right, so now we can send a big, long, ridiculous exponentiation question to BC and have BC execute that. Or not. I forgot my new line, didn't I? No. Oh, there it is. Okay, that was a good exercise. All right, so so that popen executed and started running BC, and BC is running as its own process. I'm never going to get back to the start of this, am I? Right? And even though our main program exited, we could see BC was still sitting there running. You notice its parent's process ID was 1, right? Because the process that had started it, which was P1, exited, and so this process became orphaned and was adopted by process ID 1, which is the init process. And that shell, 31853, which was created by the pipe, was running the BC command 31854. And so even though our program exited, BC was still running. And then a few seconds later, it finished its ridiculously long calculation and printed out the answer. And then BC exited. And now, you know, it's just the shell in my current command. So this is true. Well, if you have multi-cores, it's true parallelism. It's true multitasking, at least, right? Two things happening at the same time. More than two things. All right, so we can I'll save this code too. We can put this stuff to good use. Let's get rid of some debugs. All right, so we're going to make an interactive calculator here. It's going to say enter a calculation. It's going to call fgets to read that calculation from us. And then we're just going to send that calculation to that thing that we're trying to calculate. We're just going to send that to BC. So we'll send buffer. It will already have a new line at the end. And then we'll prompt the user again. And then when the user hits Control D, we'll say goodbye. And I'm doing an extra new line here in the beginning because I'm not doing a new line here. And I want my goodbye to come out on a new line. So there's P2. I could also do an F puts. All right, so P2, so enter a calculation. Let's do 2 plus 2. 2 plus 2 is 4. Let's do, 7 times 8. Or 78 times 8. And 78 times 8 is 624. But this is asynchronous, right? In particular, BC is printing out its answer before my C program gets back up to the top and says enter a calculation. And so this is another interesting aspect of working with multiprocessing is, things really are kind of independent. They're just kind of off doing their own thing, and if we need these things to be coordinated, we've usually got to set that up ourselves, right? So right now, BC is completely independent, and if it can get out an answer before we can get back to the top of our loop, we get, what looks like kind of strange behavior. All right, so let's look at the other direction. Let's look at input. So let's execute some command like date and say read. All right, so we're going to run the date command. We want to read the input into our program. So I'm going to say, let's read into our buffer from this file pointer. And let's just print out inside delimiters what we got back from reading that file pointer. And then when we're done, we'll close the file pointer to make sure that that command is exited, and we'll say goodbye. So here we're going in the opposite direction. We're going to run a command and we're trying to read input from what that command is generating. So, and I feel like I'm missing something here, but let's open up a command for reading. We'll do fgets and read from that file pointer, that pipe. We'll print out the value we got until it returns null, and then we'll close the file pointer. Right, so I run P3 and it tells me the pipe returned, and there's what I got. And if I run it again, I get a slightly different time. Now this is really cool because it means inside my C program, you know, after I execute this and this, I have a string that that contains, you know, date time information, which, you know, could be useful. If I do ps-lf, right, here's what I got back from my program. So my ps command returned 5 lines, right, a header, information about my bash shell, information about this program that's running right now, that's myself, the shell process that was created by P3, and then the command that was executed by the shell process. GCC is, yeah, so hopefully it's not the same time. Yeah. So I don't know if I've told you the story or not, but I did a little modification to our operating system on our school's computer. I found the spot in the OS where, because I was curious how time gets managed, right? And it turns out every 10,000 nanoseconds a interrupt fired and something got incremented to say, hey, 10 microseconds had passed, right? Maybe it was 10 milliseconds. But it would bump up this count of how much time had passed since you know, since some starting point, and it would use that to calculate the time. And I was curious, you know, what if I change that to subtract instead of increment the total amount of time. So I just changed that one instruction from an increment to a decrement, right, in the OS. And it was interesting. It was interesting that the system survived for about 30 seconds after that, before it crashed. But, you know, the first thing that I noticed was I was in VI and I typed a parentheses, some other stuff, and when I hit the right paren, it went to match the left parentheses, and it never came back to the right parentheses. Well, I was supposed to go back and match the left parentheses, show you that for a second, and then return. Well, I was waiting for a second to pass, but time was running backwards. So that second never passed, and so my VI session died. And you know, things like that start happening. So I don't know what actually made it crash, but something, you know, noticed an anomaly that was unacceptable. And usually when a system brings itself down, it's because it's discovered some kind of unexpected situation that it considers severe enough that, like, okay, we're going to panic and just, you know, start over again. Yeah, so that's fun stuff you can do on your own system. Don't do it on someone else's system. All right, so yeah, so we can read the result of Unix commands like this, right? Which can be useful. And this could be a program, right? I could run you know, the P3 program. That would probably crash my system. But I can run a C program. I could run a bash script. I could do, you know, anything that I could do from the command line pretty much, and grab the output of that command here and have it available inside a C program. All right. So popen is a kind of quick and dirty way to either run a command and supply input to it, or run a command and read output from it. And a lot of times that's enough. But sometimes we want more control. In particular, sometimes we want to do bidirectional I/O with a command. What's the significance of January 1st, 70? I know that's the epoch for Unix systems. So there's a date command that'll tell you, how many seconds have passed since January 1st, 1970. So let's look at a different way to run a process from a C program. So fork and execl. And execl is one of a number of function calls that usually start with exec. So there's execl, execl p, execl e, exec v, exec vp, exec vpe, right? A number of different ways that we can call this, but they all basically do the same thing. They're used to execute a set of code from a C program. So this is 100 times weirder than forks. So let's just write some code and then we'll talk about it. All right, so we'll print a message first saying I'm here, so we know that we're here. All right. And we're ready to do our execl. All right. So we're going to say execl date. I'm going to get this wrong the first few tries. All right, so we're gonna execute this execl function. We're gonna pass it the command date. I don't know if we're gonna need a path for that. And then we're just gonna pass it null, and we'll see if we can get away with that. I'm gonna need to include some stuff, and I'm gonna need null. Unistandard. I've got unistandard. Null argument where non-null required. Once I get this to work, then I'll tell you why it works. Alright, that may work, or it will blow up horribly. Let's see what this does. Ready to execl, done with execl. Okay, that didn't work. But that worked. All right. So, All right, so here's what we're doing. We're specifying a path to a command that we want to execute, and that's got to be a fully qualified path, so /bin/date, for example. And then we're specifying the argument list, right, that we would have for, if we were picking up argc, argv. So I'm putting in argv bracket 0, which is the name of the command, and then I'm putting in a null for the third argument. And so this should say, ready to execl. It should execute /bin/date, and then it should say done with execl. All right. When I run it, it says I'm here, ready to execl. It executes the date command. It never printed that message saying done with execl. Right? It never got to that last statement. So it did the date, but it didn't do this. All right, so what's going on with this? So let's do this. So PS is under /bin. So let's go ahead and do system PS first of all to see the process state, and then let's go ahead and use execl on PS. Alright, so this is the weird part. Here's my bash shell. That's not going to be interesting. 29263. Here's my command P4, which I ran. That was process ID 1263. That's my program that I ran up here when I said P4. And that created a shell, and that shell created the PS command. Alright, we've seen that before. We expected that. But then we said execl PS. And that ran the PS command, but look what the PS command outputted. There's the command PS executing, but what is its process ID? 1263. 1263 was the process ID of P4, the command that I ran from the command line here. Same process ID, but it's no longer the P4 command, now it's the PS command. So what has happened is, I said P4, P4 started running. When we do the execl, P4 changes. It morphs into a different command. And its whole essence basically becomes something completely different. And after we call execl, P4 is no longer executing. The command that we gave as the argument is now executing. And you can see that here because 1263 was P4, but then a little while later, the same process ID was now running the PS command. And you can make harmony with that with the fact that after we did this exec, this printf never happened. Because once we do this call to exec, this program is gone. Right? This process is no longer running this code. So I don't have a good way to draw this, but basically, you're going along. Here's some process ID. You're going along, minding your own business, right? Your name's Nick, and you're getting your coffee and stuff like that, and you execute an exec. And exactly the same process, you're wearing the same clothes, the same shoes, you look the same, but now you're someone completely different, right? Now you're a PS command or a date command or something like that. So exec is the way that we execute a process at a low level. Fork is the way that we duplicate a process, but exec is the way that we actually execute a process. And it says, let's go to this file, /bin/date, for example. Let's read the executable code out of there, all the information about setting up memory and stuff, and let's load that into ourself. And after exec finishes, this process has taken on the essence of this other executable file. And it is this other executable file now. So that's maybe a weird thing to try to get our brains around, but that's how processes come into existence. So we do a combination of these things, right? You've got your main program coming along, and then at some point it does a fork, and so you've got your original main, and you've got your main, which is a clone. And then it does an exec, and now it's, running some new program. And at that point, you've got two totally separate processes running. You've got your original main program, but you've got some new process created by fork that's running potentially some completely different set of code that it pulled in by doing an exec call. So that's how we can create processes that run things other than just an exact copy of ourselves. And this is actually how processes come into existence on a Unix system. When you are sitting at a bash shell and you say date, right? It's not the bash command that's executing date. It's a runnable program called date. And so bash forks a copy of itself, and then the copy does an exec to start executing this other program. All right, so the other piece of the process is inter-process communication. And the question of how can our main program talk to this new program, and how can the new program send information back to our main program? And this is done through something called a pipe. And we use pipes from the command line. We just type the vertical bar to pipe commands together. But pipe is a callable function, chapter 2 function, so low level, that basically gives us a conduit with two ends that are connected to each other. So when we call pipe, we get back this memory-based pipeline with two ends, and what we write into there comes out there. And remember, when we fork, we create an exact copy of the original. So if we create a pipeline in our original thread and then we fork, both threads will still have that pipeline. And when we exec, things that we have open for communication will still be available to that new process. And so we can also set up something so that in this new process, it's standard out, for example. Instead of going to the usual standard out, we'll go into this pipeline. And then our main program can read from this end of the pipe and see what this program is producing on standard out. And we create another pipe that we use for the main program to write into. And so we have standard out feeding into this, and we have this end feeding into standard in. And now the main program can write into this pipe, and this command that's running over here will read standard in, but actually be reading whatever main sent. And so we can set up two-way communication. All right, that's a really rushed presentation, and we are out of time, and we are done until next Monday. So, but we'll play around with this a little more next week, and then we'll wrap up the course for fall. So have a great week. Stay safe. Enjoy the holidays, and I will see you on Monday. Thank you. Yeah, and happy Thanksgiving.